Okay, we are recording. We're in the Module 5, Session 1 webinar. So Module 5, we're in the second half of the class. And tonight we're going to talk about velocity and acceleration. We're going to revisit implicit differentiation and talk about critical values. So let's get started. So position, velocity, and acceleration are all related. If we are given the position function of, let's say, a moving object or a moving particle, so at any given time we're given the position or the location of this object. The rate of change of the object, which represents how fast the object is in one place versus another, is the velocity function. So we can get the velocity function by taking the first derivative of the position function. And the rate of change of the velocity, or the derivative of the velocity function, will give us the acceleration function. So if we're given a position function, we can always find the velocity and acceleration function, assuming that it exists. So let's do some examples. So we have a ball that's thrown vertically upward from 2 meters off the ground with an initial velocity of 4 meters per second, and the position function is given as s of t equals 2 plus 4t minus 4.9 t squared. So they gave us the position function, and we're asked a few different questions. So how long does it take for the ball to reach the highest point? So thinking about this ball, I throw the ball up in the air. At some point, it's going to return to the ground. So we want to know, what is the highest point that this ball reaches? What do we think? How can we find out what the highest point this ball reaches? Do we know anything about the highest point? Very good. The ball is thrown up in the air, and at some point, it's going to slow down to 0, and then it's going to fall to the ground. So we know that at the highest point, the velocity is 0. So what we can do is we can first find the velocity function. And that's just the first derivative of the position function. So when we take the derivative, the 2 goes to 0, 4t becomes 4, and then take the 2 to the front with the 4.9, and subtract 1 from the exponent. So we get that the velocity function is 4 minus 9.8 t. So we know that when the velocity function equals 0, that's where the ball has stopped traveling up, and it stopped and it falls back to the ground. So what we can do is set that equal to 0. And what that's going to tell us is when the ball is at the highest point. It's going to tell us, because we can solve for t. So I can move the 9.8t to the other side. And I get t equals 0.408. Do we know anything about the units of that value? Well, we were given meters per second. Good. So since this is time, it's just going to be seconds. The velocity represents meters per second. The time is 0.408 seconds. So this doesn't tell us the highest point, but it does tell us when the ball is at the highest point, or how many seconds after the ball is thrown it's at the highest point. So what can I do with this to figure out what the value of the highest point is? Well, I know S of t. That tells me the position of the ball at any given time. So what I need to do is plug in 0.408 for t, because that's when it's at its highest point, and that will give me the value of the highest point. So let me go to the next page. So we know S of t, the position function, is 2 plus 4t minus 4.9 t squared. And I know that at 0.408 seconds, the ball is at the highest point. So I just plug in 0.408. And that will tell me what the position is of the ball at 0.408 seconds, which is the highest point. And it's 2.816. And the position function was given to us in terms of meters off of the ground. So this is measured in meters. Okay, so what I did was I know that at the highest point the velocity is 0. That's where the ball is stopped going up and is going to start falling back towards the ground. And then I can use the velocity function. When that's equal to 0, that tells me when the ball's at the highest point. And so I can take that value, that time value, and plug it into the position function, and that will give me how high the ball is off, or the highest point. We were also asked to find, so we found how long it took the ball to get to the highest point, 0.408 seconds. We are also found what the highest point is, and now we're asked to find how long does it take before the ball hits the ground. So how do we find out how long it takes for the ball to hit the ground? Is there anything we know about the ground in terms of the position function? Very good. So the ball initially starts at 2 meters above the ground. So what's the height on the ground? Sorry, just rewriting the question. Well, here's the ground. The ball starts at 2 meters above the ground. It's thrown up in the air, and then it falls back to the ground. Do we know anything about the height on the ground? Very good. It's 0. So we're 0 meters off the ground when the ball hits the ground. So we know that S of t, the position of the ball, equals 0 on the ground. So what we can do is we can set our position function equal to 0, and that will tell us when the ball, or how long it takes the ball to hit the ground, how many seconds after the ball is thrown to hit the ground. So I'm going to set the position function equal to 0. So we have 2 plus 4t minus 4.9 t squared. And I set that equal to 0. Again, the height on the ground is 0. And unfortunately, this does not solve, factoring this isn't very straightforward. So we would use the quadratic formula to solve this. Let me go to the next page. So the quadratic formula is negative b plus or minus the square root of b squared minus 4ac over 2a. And a, b, and c, a is the value in front of the squared term, so in this case negative 4.9. B is the value in front of the t term, and c is the value that's just the constant. So we can plug those into the quadratic formula, and we'll get 2 answers, which is pretty typical with quadratic equations. Not always, but pretty often they have 2 answers. One of the values that we get is negative 0.35. The other one that we get is 1.17. How do I know what the answer is? Well, we're talking about time, and time can't be negative. So that eliminates one of our answers. Okay, so that means that it takes the ball 1.17, and since we're in meters per second, that was all of the information we were given. This is, since it's a time, takes 1.17 seconds for the ball to hit the ground. If we had gotten two positive values, so sometimes depending on the question, it's possible that the ball was thrown from the ground rather than 2 meters above the ground. If that's the case, you'll end up getting a t equals 0 value, which means initially the ball was on the ground, and then the other t value is saying how long it took for the ball to reach the ground after it was thrown. So it's possible to get a t equals 0 and a t equals another value. It's just in this case, the ball started at t equals 2 meters, or excuse me, not t equals 2. It started at position of 2 meters above the ground, so we only had one t value. And time can't be negative, so that's how we knew that wasn't an option. Okay. Let's revisit implicit differentiation. So implicit differentiation was when we had a function that was not explicitly a y equals function, but we were asked to find the derivative, so dy dx. So before, something, for example, like x squared plus 2y squared equals xy, something similar, where if we were asked to find dy dx, this was our first types of examples of implicit differentiation. Part 2 is very similar, except for now, instead of being told that y is a function of x, we are told that x is a function of t and y is a function of t, which means they are two functions, and we weren't given those functions, but they're two functions defined as some other variable. So where this is going to show up pretty often is parametric equations. If you go on to Calculus 2 or even many physics courses, deal with parametric equations. It's just another way to define, for example, particle travel, or to graph functions is to have an x and y function that's another variable. And that's what we have here. So x is a function of time, and g is, or I just said time. It's pretty often that it's time. It doesn't have to be. So x is a function of t, and y is also a function of t. So we are asked to find dy dt. So just like when we were doing examples like this, we were asked to find dy dx. We found d dx of each term. So in this case, we're asked to find dy dt. So we're going to find the derivative with respect to t of each term. So I have d dt of x squared plus d dt of 6y squared plus d dt, just taking the derivative of each term with respect to t, which is what this is down here in the denominator. It's telling me what variable to take the derivative with respect to. And then on the right, I have d dt of 36. So the easiest derivative to take is on the right side of the equal sign, because we're taking the derivative of a constant. So that's just going to go to 0. And then these three derivatives. Let me go to the next page really quick and just write this out again. Okay, so on the right side, we get 0. Derivative with respect, or of a constant with respect to any variable is 0. How this changes from before. Before we were finding dy dx, and we weren't given y explicitly as a function of x, so we could say we could use the chain rule. Now we just have to use the chain rule on both variables. So when I take the derivative of x squared, I get 2x. But we were told earlier that x is a function of t. We weren't told what it was, but we were told that it's a function of t. So that means I have to use the chain rule. So I took the derivative of the outside function, so I moved the 2 to the front and subtracted 1 from the exponent. But now I have to take the derivative of x with respect to t, which all we know about it is that it's dx dt. If we were given what x was, say we were given x equals 3t squared plus 5, we could take the derivative of that, but we weren't. We were just told that it's a function of t. So all I can say is that it's dx dt. What about the second term? What do we get? Well, the same idea. I'm going to take the 2 to the front and subtract 1 from the exponent. So I get 12y, but what else do I need? Very close. I need dy dt rather than dx dt, but very, very good. So the derivative of y with respect to t. So I took the derivative of the outside function, which was the 6y squared, and then I have to take the derivative of the function y, which all I know is that y is a function of t. So when I take the derivative of it, I just get dy dt. And the derivative of 6y, well, the derivative of 6y, I'm just left with 6. But again, because y is a function of t, I have to use the chain rule, which says times the derivative of the function y, and all I know is that it's dy dt. We were also given some other information. We were given that dx dt is 2, x equals 6, and y equals -1. We were given that dx dt equals 2, x equals 6, and y equals -1. Just making sure I copied those down correctly. And now we have everything that we need. What we're trying to solve for is dy dt, so we can plug all the other values in. So we have 2x, or 2 times 6, value for x, and then dx dt we were told is also 2. So all of this, I just plugged in the values that we were given there. And then plus 12 times y, so 12 times -1, and dy dt we don't know. We're actually solving for that, so that's, we don't know that, it's unknown. Plus 6 dy dt, again, we don't know. And all of that equals 0. So I plugged in the x value, I plugged in the y value, and I plugged in dx dt because those were what we were given. Let me go to the next page and rewrite that. And now we can simplify and solve. So the first term we end up getting 24, and then minus 12 dy dt, just simplifying the constants, plus 6 dy dt equals 0. And I'm solving for dy dt, so I can solve for it basically the same way I would solve for x. I'm going to combine all the terms and move everything. So I can combine these two terms. So I'd have 24 minus 6 dy dt. So I have -12 plus 6, so I get -6 dy dt equals 0. And I can move either of these terms. I will add the 6 dy dt over to the right. So I have 24 equals 6 dy dt, And the last thing to do is just divide over the 6. And I get 4. So what this would represent, if we were talking about, let's say, an object that's traveling in the x and y direction at different rates. So this would represent the rate of change of the y value with respect to time. So if we had a particle traveling on an xy plane, it's going to represent the rate of change of the y value with respect to time, which may be different than the rate of change of the x value with respect to time. All right. Let's do another example similar to this one, but a little bit more information is given. Is increasing with the rate of 9 centimeters per second, and the width of the rectangle is decreasing with a rate of 7 centimeters per second. When L equals 3 and W equals 8, find the rate of change of the area, perimeter, and the length of the diagonal. Okay, so there's quite a bit going on in this question. The first thing that I do whenever I see a word problem is I try to draw a diagram if I can, and I write down everything that I have and anything that I know and what I'm looking for. So let's say I have this rectangle. And I'll label this the width and this the length. It's okay if you have them in the opposite locations, it does not matter. So we were told that the length of the rectangle is increasing with a rate of 9 centimeters per second. Do we know what that would represent, variable-wise? Well, it's the length and how it's changing with respect to time. So it represents dl dt, the rate of change of the length with respect to time. And we were told that it's increasing with a value of 9 centimeters per second. So one thing that I know, why I knew that was dl dt, is because it's a rate of change. So it represents a derivative. Okay, we were also told that the width of the rectangle is decreasing with a rate of 7 centimeters per second. So what does that represent? Good. So we know that dw dt, and because we were told it's decreasing, is negative 7. Or negative dw dt is okay too. So it's decreasing, which is why it's negative. And we were also told that L equals 3 and W equals 8. And then they ask us to find the rate of change of the area. So let's just start with the area, and we'll deal with the other two in a minute. What do I know about the area of this rectangle? Perfect. Length times width. So the area of the rectangle is length times width. What are we actually trying to find? We're trying to find the rate of change of the area. So basically, how is the area changing as the length and the width are changing? How's the area changing? So variable-wise, what would that be? We want to find dA dt, how the area is changing with respect to time. So basically, we're using implicit differentiation because area is a function of length and it's a function of width. and they're both changing with respect to time. So this is an example of the one we just did, except for we have some context to it. So I know the length is a function of time, and I also know the width is a function of time because at different times there are different values because we were told that they're changing. So if I did what I did on the last example, calculate the derivative with respect to t of each term, on the left, the derivative of a is just 1, but with respect to time, we have to use the chain rule. So that's how we get dA dt. Let me go to the next page really quick. So we know area is length times width. We're trying to find dA dt, the rate that the area is changing with respect to time. And so we took the derivative with respect to t of each term. And we know that the length is changing as a function of time, and we also know that the width is a function of time. So I'm going to have to use the chain rule, so implicit differentiation. How am I going to take the derivative of the right side? On the left side, I have dA dt, and that's what I'm trying to find. So what about the right side? Well, I have two functions, and they're multiplied together, and they're both a function of t, which means I have to use the product rule. So if I do what I did before, let's say that I say that this is L and this is W. What's the derivative of L with respect to time, or with respect to t? Well, derivative of L is just 1, but remember the chain rule says we have to take the derivative of the inside function, so we get dL dt. And the same thing with W. We get dW dt. And then we can cross multiply. So I have L dW dt plus W dL dt. And again, the chain rule has to be used because both of these are a function of time. The length and the width are both changing with respect to time, which means they're a function of time, or a function of t. So when I take the derivative, I take the derivative of L, for example, which is just 1, but then I have to take the derivative of the inside function, so that's dL dt. We weren't told what the function, we weren't told these two things, we were just told their values for how fast they're changing. So we now have an equation that models how the area is changing with respect to time. We were told that all of this information here, so we can go ahead and plug all of those values in, and we'll have the rate of change of the area with respect to time. Let me go to another page. So we found that dA dt is L times dW dt plus W times dL dt. And we were given that dL dt, just rewriting all of the info that we were given. dW dt, we were told, is -7 because it's decreasing. And the length and the width at this point were 3 and 8. So I can plug all of these values in. Sorry, I just wanted to make sure I didn't copy anything down wrong. I just wrote the wrong number though. Hold on. Okay, so L is 3, dw dt is -7, plus w, which is 8, and dl dt, which is 9. And I get 51. So the rate of change of the area with respect to time is 51. So it's positive, which means it's increasing. The area is increasing with respect to time. Okay. We were then asked to calculate how the perimeter is changing with respect to time. So let me just rewrite the question. So how is the perimeter changing with respect to time? It said what is the rate of change of the perimeter, which is basically saying how is the perimeter changing with respect to time? So as the length and the width are changing, the perimeter is changing too. So what do we need to know? Well, when we were trying to find the rate of change of the area with respect to time, we needed the equation for the area. Great, 2L plus 2W, and you can always draw a rectangle. Width, length, the perimeter is the sum of all the sides. So we have two sides of length L and two sides of width W. So 2L plus 2W. So that represents the perimeter, and we want to find out how quickly it's changing. So what are we actually trying to solve for? Well, we want to find the rate of change of the perimeter with respect to time. Perfect. So the rate of change of the perimeter with respect to time, dp dt. So I'm going to do the same thing I did on the last one, take the derivative of each term with respect to t. And that's what this represents in the denominator. dt in the denominator is telling us what variable we're taking the derivative with respect to. It's kind of like when we had dy dx, that's saying take the derivative of y with respect to x. So in this case, we're taking the derivative of each term with respect to t. So d dt of each term. The perimeter is actually a little bit nicer because on the right side, we don't have two functions multiplied together. We just have 2L and 2W. So we don't have to use the product rule. So on the left, we get what we're solving for, just like we did with the area. And on the right, derivative, the constant stays where it is. What's the derivative of L? Good. Excellent. Derivative of L is 1, but then times the derivative of the inside function, so it's just dl dt. Okay. And then very similar with the second term. The 2 stays where it is, and the derivative of w with respect to t is just dw dt. And we were given all of these values. We were given dl dt is 9, and we were given dw dt is -7. And I can plug those values in. And I get 4. So this represents how the perimeter is changing as the length and the width are changing. And it's positive, which means the perimeter is increasing. And the length is changing by a more positive number than the width is changing, so that makes sense. Okay. Do we know the units of that? Let's talk about that for a minute. Do we know any information about the units? Well, what are the units of the perimeter? If we go back to the units that we were given, the length and the width were changing as centimeters per second. So what do we think about this? So it would just be centimeters per second because the perimeter is changing, and the perimeter's units are just centimeters. And one thing that you can do is look at what we have. The perimeter is measured in centimeters, and t is measured in seconds. So we would just get centimeters per second. The second derivative would be centimeters per second squared, though. Okay, we had one more part of this question, and it was asked to find the rate of change of the diagonal. So let me just draw our rectangle. And again, it does not matter which side you label as width or length. I typically label how wide the rectangle is as width, and the height of the rectangle is L, but it's okay either way. So we were asked about the diagonal. How fast is the diagonal changing as the width and the length are changing? So the diagonal is represented right there. So let's just call this D for diagonal. So just like the last ones, we're trying to find the rate of change of the diagonal, so how the diagonal is changing. So this is what we're trying to find. What do we know? What can we start with? Well, do we know how to find the length of the diagonal? Well, technically we've got a right triangle here, so we can use the Pythagorean theorem, which says that d squared equals L squared plus W squared. So we could take the square root of both sides, because the Pythagorean theorem, to solve for just d, but we're trying to find this value, so we really don't need to. I can take the derivative with respect to t of each term, and it makes it actually much easier to take the derivative. So the Pythagorean theorem got me that. The side of, or the square of each leg added together equals the square of the hypotenuse, or the diagonal. So if I take the derivative with respect to t of each term, and the good thing again, I don't need the product rule again, like I did on the first one. So the derivative with respect to t of d squared, what do I get? Good? Is there anything else? Do we need to use the chain rule? Is the diagonal changing with respect to time? It is. So because the diagonal is also a function of time, I have to again apply the chain rule, so I get dd dt. And on the right side, 2L, and again, L is a function of time, it's changing with respect to time, so I get dL dt, 2L dL dt, plus 2W dW dt. So I took the derivative of each of the outside functions by taking the 2 to the front and subtracting 1 from the exponent, but each of these variables, so d is a function of time, L is a function of time, and W are all functions of time. So because they're functions of time, I had to apply the chain rule to each of them. One thing that I can do, and you don't have to, but you can if it helps, each of the terms have a 2, so you could divide each term by a 2. It doesn't matter, it works out exactly the same way if you don't. So we need all of the information. Let me write the equation on the next page. So after I cancel the 2, I have d dd dt plus L, excuse me, not plus L, equals L dL dt plus W dW dt. I canceled the 2, and again, you don't have to. It works out the same way if you don't. I know that L is 3. I know dL dt is 9. I know W is 8. And I know dW dt is -7, just writing all of the info that I know. I know this is what I'm trying to find, dd dt, so that's a question mark. That's what I'm trying to find. What is d? Do I know the value for that? I need it because I have two unknowns without it. So I do need to know what the value of this is. So I'll put a question mark for right now. Is there a way that we can find it? What do we know about the diagonal? Well, we know that it's d squared equals L squared plus W squared by the Pythagorean theorem. So can I find it? Yes, I have W. I know W is 8. And I know L is 3. So I can use those two to find the value of D. And I have to because I need only one unknown in my equation. And right now I have 2. So D squared equals 3 squared plus 8 squared. So I get D squared equals 73. And I just need the value of D. So I'm going to take the square root of both sides. And 73 is not a perfect square, and I can just leave it as it is. And we don't apply a plus or minus here just because this is a length, so we don't need the negative value. But typically when we take a square root, we apply a plus or minus. So now I have the value of the diagonal at this specific length and width values, and I can plug that in. As the square root of 73. And then I can simplify. Okay, so let me go to the next page, just rewrite this. So we know that the value of the diagonal is the square root of 73. dt we're trying to find. I know L is 3. I know dl dt is 9. I know W is 8. And dw dt is negative 7. So on the right side, I end up with negative 29. And what can I do to solve for dd dt? Just divide over the square root of 73 to both sides. And we could simplify that to a decimal if we wanted to. Typically, we would leave our answers as exact values, so we wouldn't need to write it out as decimal, but if we wanted to, just to get an idea. It's about negative 3.39. So in this case, we get a negative value, which just means that as the width is decreasing and the length is increasing, the diagonal is decreasing at this particular time. Oops. Okay. So implicit differentiation basically just says if our variables are defined in terms of another function, so time, for example, in this case, and time is a typical parameter that we work with. So our variables here, L and W, were both changing with respect to time, as well as the perimeter and the area and the length of the diagonal were all changing with respect to time, which is why each of these derivatives had to use the chain rule. We had to take the derivative with respect to time. And that's why those are there. Okay, let's move on. And the last topic we'll talk about tonight is critical points, or critical values, they're often called. So a critical point is a point that has the potential to be a local maximum or a local minimum. It can also be thought of as the endpoints of a domain, which we'll talk about later. But the typical definition of a critical point is it's a point that has the potential to be a local maximum or a local minimum. And what I mean by local max versus local maximum and local minimum is right here. This is a local minimum. It means that it's the lowest point of all the points around it. Because really, this point over here is lower, so that's more of a minimum than this point is. But it's a local minimum because it's the lowest point of all the points around it. We also have a local minimum here. And then we have a local maximum here and a local maximum here. there's something called an absolute maximum, or another word for it is a global maximum. We'll talk about those later as well. But right now, just going to talk about a local maximum or a local minimum. What do we notice about these four different places? Do we notice anything that they all have in common? Very good. They're all a point where the graph is changing direction from either decreasing to increasing or increasing to decreasing. Can we say anything about the slope of the tangent line? Great. The slope of the tangent line on each of those places is 0. They're all a horizontal line, so they're all 0. So what that means is at a local maximum or a local minimum, the slope of the tangent line needs to be 0. It doesn't necessarily mean that if you do get a slope of a tangent line of 0 that it is a local max or min. It could be something else, which we'll also talk about later. But if it is a local max or min, we know that the slope of the tangent line has to be 0. So how do we find the slope of the tangent line? Very good. The derivative. So if I take the derivative of the function, that tells me, that gives me the way to find the tangent line slope. And typically I'd plug in an x value, but now what I'm going to do is I'm going to set it equal to 0 because I want to know what x values have a slope that's 0 of a tangent line. So we'll do some. Let's try this example. It says sketch the graph that can represent the following function. And we were given x values of a, b, and c. And then we were given f prime of x values, so the derivative values. We have 0, 0, and 16. So we weren't given much information, which is why it says sketch a graph that can represent this, because we could all come up with a different graph that represents this data. So let's say I label A here, B here, and C here. Unfortunately, we can't just plot the point 0, 0, and 16 because that doesn't represent the function, that represents the derivative of the function, which is different. So it's telling us basically at x equals a, the derivative is 0. So that's what this first part is saying. At x equals a, the derivative is 0, which means there's a potential local max or local min there. We don't necessarily know which one it is yet. So let me look to the next one. Well, we have the same situation. At x equals b, we have another slope of a tangent line of 0, which means it could be a local max or a local minimum. Or another way that it was said earlier is turning directions. So at these two places, the graph is changing direction. We just don't know which one is which. This is where we go to part C, or x equals c. We're told that the derivative is 16. Going back, what does a positive first derivative represent? What does that mean in terms of the graph? Great, it means the graph is increasing, and kind of like the last example with implicit differentiation that we did, when the area, we got a positive value for dA dt, which meant the area was changing positively, it was growing or increasing. That's what this means. It means the graph is increasing at x equals c. So if I draw the graph increasing at x equals c. And then this is kind of, I have to go backwards. So I know at x equals b, the graph changes directions. And then I know at x equals a, it also changes directions again. So this is an example of a graph that could represent the information that we were given. So let me just say that one more time. So at x equals c, we got a value of the first derivative is 16, which means the slope of the tangent line at that point is 16, and all we really care about is that means it's increasing. At this point, it's increasing. And we know that at x equals b, the graph is changing directions, which means, or the slope of the tangent line at that point is 0. So those two represent a slope of 0. One thing that we couldn't have done, and the reason I started over on the right side rather than on the left side is, just want to mention this really quickly. If I had drawn it this way, where the graph is changing direction at A and changing direction at B, well, what that means, unless it changes directions again between B and C, which we weren't given any information about that, is this graph would represent a negative value at C. And we were told that C is positive. So that's why the graph up in the right corner is not right. It wouldn't work because that would represent a negative derivative for C rather than a positive derivative. And there's many different ways you could have ended up with the same. So for example, you could have had A to the left of the y-axis, all three of them to the left of the y-axis. There's many different answers that could work. But this is a graph that would represent the information in the table. And you don't have to draw the tangent lines. I just did to help us understand why. All right, I think we have one more example. Yes, I want us to find all the critical points given this function. So f of x equals 15x squared minus 2x to the third. Find the critical points. We know the critical points represent a potential local max or min, which means the slope of the tangent line is 0. So what we need to do is set the first derivative equal to 0. So I want to find where there's a potential local maximum or minimum, which means the graph is changing directions, so the slope of the tangent line is 0. Well, the slope of the tangent line is the first derivative. So I take the first derivative, and I get 30x minus 6x squared. And I'm going to set that equal to 0. So I have 30x minus 6x squared equals 0. And one thing that I recommend doing when we're solving questions like this, where we're trying to find x values, rather than move the 6x squared over to the right, if you move the 6x squared over to the right, you might think to cancel the x, and we can't cancel the x because we would miss out on one of the x values. So what I mean is, on the left side, is there anything I can factor out? Good. They both have an x. They also both have a 6, so I can factor out a 6x. And then I'm left with 5 minus x equals 0. And at this point, I can break this up into two parts and say 6x equals 0 and 5 minus x equals 0. So I get two values. I get x equals 0 and x equals 5. So had I, just want to quickly go back for a minute, had I solved it this way, and then if I had said, okay, I can cancel that, then I would have had 30 equals 6x, which would have only given me the x equals 5 answer. And the reason I can't divide out an x is because can x be 0? Yes, in fact, it is 0 at one point. So if x can be 0, that means if I divide by it, I'm dividing by 0, and I can't divide by 0. So one thing that I typically do is I just don't divide variables. I can divide constants, I just don't divide variables. That's why I instead factored out the 6x, and then I got both answers. So what those two values tell me is at x equals 0 and x equals 5, there's a potential critical point, or excuse me, a potential local max or min. So that tells me where the critical value is. It depends on how the question is worded. We were asked specifically to find the critical points. Which means our answer is likely going to be an ordered pair. So because we were asked specifically for points, we want to find the ordered pair. So our original function was f of x equals 15x squared minus 2x to the third. And we took the first derivative and found that the critical points are at x equals 0 and x equals 5. If we wanted to get points, so an ordered pair, how would we get the y values? Very good. Plug in for x. And one thing I want to mention is when we're trying to find the y value, we plug back into the original function, not the derivative function. The derivative function is just used to find where the critical points happen. It doesn't tell us the actual y value, it tells us the x value of where they happen. So if I plug in 0, I get 0. So one of my critical points is at the point 0, 0. And if I plug in 5, I get 125. So I get the other critical point is at the point 5, 125. So if you were asked for the critical value, typically you would just leave it as x equals. The only reason I found the actual ordered pair is just because we were asked to find the critical points. So that's why. And I believe that's it for tonight. On Thursday, we're going to talk about L'Hopital's rule. So L'Hopital's rule is used when we're calculating derivatives, excuse me, not derivatives, I'm sorry, when we're calculating limits. And when we calculate limits, there's something called indeterminate forms. So there's several different forms that our answer might end up as. So one that we've actually worked with at some point is 0 over 0. When we got an answer of 0 over 0, when we were working with limits before, we factored and did anything we could to simplify. But we could also apply L'Hopital's rule, and that we will talk about on Thursday. It involves taking derivatives, but we will talk about that on Thursday. All right.